Okay, so this is the third module of basic neural networks. So what we're going to cover is the Backprop, the stochastic gradient descent method used to train these neural network models. So we actually show you this block view at the end of logistic regression. So we can just write them as summation and a sigmoid and actually concatenate with this error loss function at the end also as a block. And then we later put them together, put the neuron view to kind of represent the combination of dot product layer, summation layer, and the sigmoid. And we can think about this is our first layer function, like F1. This is our second layer function, like F2. So I'm going to reuse this notation many, many times in the future, next few slides. All right, so we can also think about this multi-class, I mean, the whole pipeline from the X into the last E, this error. We can think about this as the first F1, F2, or maybe more better is this parameterized view. So there's X, and then with this W, so I'm feeding the X by some function parameterized by the W1, I got H1. And again, here is W2, H2, then here there's a W3, and this is actually a softmax layer. This give me Y hat, and then I'm not stopping, I give one more, and this actually this some kind of error function. This give me E. And this E takes input is the Y hat and the Y truth. So this is the whole pipeline actually is the forward step. And for this multi-class simple MLP layer model. So I already showed you, right? So we can actually think about every possible neural network models. I mean, from this kind of layer to layer, feed forward step, and there's a lot of middle variables in the middle. And there are middle variables, there's also middle parameters. And in the forward step, you need to calculate all the middle, those variables. Yeah. So in this case, I need to have all the H1, H2, and the Y hat, and then give me the E, the error. All right, so, and we actually try to connect stochastic gradient descent and how you use it in logistic regression in the last time, in the last class, and basically the same, right? So in the basic regression, you have the J theta function, and here we just replaced it. I mean, when we do binary classification, we just replace into that cross entropy loss. And all possible kind of loss functions. And there's one difference is the neural networks has kind of layer-wise structure, right? So we can, like the basic stochastic gradient descent, we just treat them as a joint W parameter. It's a very big parameter, W. We can use just the gradient descent method just to update almost like W, like using this W t plus 1 iteration equals the WT's iteration minus a learning rate, and then times that gradient of the last error, that error function versus my W at the tth iteration. So this is the most basic gradient descent rules, right? People sometimes also call that delta rule here. But something different is this W in the neural networks can be calculated layer by layer just by the nature of how they look, how this model really is, because there's a layer-wise structure. It's a function composition. When you have multiple function composed together to build the big models, the simplest rule you can normally use is the chain rules. So I hope you still remember. So like, let's think about assuming my final function f, actually I showed you, right? Neural networks can be showed as this error function. This error function can be showed as a composition of maybe F4, like there's F4. In this case, so this is like maybe, let me see. So this is F1 function, this is F2 function, and this is the F3 function, and this the error function as F4. I can just write this as F4, F3, F2, and F1. And then there's X, and then, yeah, it's little here, so it's better to write here. So this whole thing is, so this is X, there's also Y truth, right? So this is your label data, XY, and you can just write it as F4 takes the Y truth and also predict the F3, right? F3, and then F2, F1, X, 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 X. All right, so now you view this as a composition of layer functions, and then it's very easy to think about chain rules, right? So because for every layer, I have a parameter related to it. For some layer, not every layer. So this has a W3, this has a W2, this has a W1. So I can think about for example, W3. So because my E function is, so there's a composition, right? So the composition here is actually versus the F4, because composition. I hope you still remember what is chain rule. And then times that F4 function versus the W3. And this is essentially, yeah, I think it may be W3. This is F3. F3, yes, because E itself is F4. And this is actually the simplest chain rule to be applied. So you can tell there are two terms here. First is this error versus F3, which essentially you're calculating this versus this. And then after you get it, and then after you get this term, you just, that's the, so let's see, you get F3, and then you can just calculate, multiply the F3 versus W3 right here, and then to get this error versus the W3, which is needed to update that W3 layer. So this is essentially the essence of Backprop. This is correct. Okay. Yeah. So so let's just see what is backpropagation. So you initialize your network parameters layer by layer with random weights. Then for all for actual training set, this is the basic backpropagation. And there's various versions like mini batch version or single sample versions. So for the most basic version, we can think you can have all the training samples. You feed the input samples to the network layer by layer by calculating all those middle outputs of each layers until the last error function layer. All right, so we already showed you. And then for the backward, you actually from the last that error layer and calculate the gradient of that specific layer to its input, and then all the way come back and feed forward, backwards feed. I'm going to show you how to do that. So forward step, it's really just X to calculate H1, H2, and Y hat, and then also get that error term. And the backward step is, so you propagate the gradient from this it's from this E versus the Y, and then so I think I have H1, H2, and then this is Y hat, and this is Y hat over the H2, and then this is the H2 versus H1, and then this is the H1 versus the W1. And you just, in each step, you calculate that local gradient and then send it to the layer right before it. And so actually this is the sigma layer, so I have an E, assuming this is the, I can calculate this E versus that. So this is, I used H before, but that's fine. I'm using the sigma now. So I got this E versus the sigma from all the layer here. And then I have this sigma versus the X, which essentially is the sigma times 1 minus sigma. And then this really gives me for E versus this X input for this specific sigma layer, and it's the multiplication from the next layer's gradient, which is sigma to the X, and which is E to the sigma, then times my own block's gradient, which is sigma to the X. So the gradient descent backprop also, what I showed you, I mean, there are many variations. So there I showed you can use all the training samples, but we actually know, I mean, it doesn't make sense for the majority of the deep learning tasks. So essentially the most used is the mini batch version. So for each batch of the input samples, you feed forward to calculate all the middle variables, and then you backprobe the gradient of the error from all the layer after me, then calculating my current output variable versus the input variable's gradient, and then do a calculation, and then I backprobe my current gradient to the layer before me. So this is really this whole backward, forward and backward, and by that way, you are actually calculating the E to the WT to whatever layer, you can calculate that, and then you can just do the update exactly the gradient descent, stochastic gradient descent based, and using the stochastic gradient descent updating delta rules. Similar to what we had in the linear regression, so the learning rate is important. So if you have high learning rate, it may just kind of blow off, right? And then what is the proper learning rate? This curve, we're always trying to draw this curve, the epoch, right? So normally the good learning curve at this kind of graphs, I mean, draw them out and to kind of check, is my current optimization doing well? And there are many great tools, and actually majority of the stochastic gradient descent tools were invented for the deep learning type of model training. And also using this train curve versus the validation curve, the differences to check. I mean, is this overfitting? Is this underfitting? So should I increase the model capacity? So everything we let you draw in the homework 2 can also be applied here. So the validation curve is easy to be plotted here. I think the learning curve is a little bit difficult because the learning curve relies you to do this varying size of the training. So for deep learning tasks, there are always a lot of training samples. So that's a little bit difficult to draw in this field of this family of models. All right, so there's some actual things like people actually use a lot to plot, I mean, for their deep learning models we did not cover. So for example, the per layer activation, that every layer's output variable H1, H2, and plot their magnitude, their variations. This can actually tell you a lot about the underlying behaviors of your model, and also plot the gradients magnitude, gradients like spatial or feature ranked variations. So those are all very great tools to sanity check your model. And also weight initialization is extremely important in deep learning. So it seems to be very not very important in our linear regression based gradient descent type of optimization, but it is extremely important in the deep learning type of optimizations. And also batch normalization. So what we covered is regularization. So essentially batch normalization, it's a implicit kind of regularization, and you add upon on your deep learning models. So it's very complicated, so I will put as extra. Feel free to read all the relevant documents I will share. So these are all very great topics. And also data pre-processing is extremely important in this domain too. So I will not talk about it. And the last thing I want to emphasize is, so the hyperparameter tuning in the deep learning or neural network type of family is extremely difficult. So because you have just so many to tune, right? You need to select network architectures, you need to select learning rate, learning the type of optimization, and what is the update type, what is the decay type, what is the regularization. It's just very, very complicated. So sometimes people see this more like an art than a principled science. So in general, use your loss function. Use this epoch versus loss, as your friends to see, to compare. And recently, very recently, people try to many groups try to tackle this problem by doing automated hyperparameter tuning, automated network architecture search. This is part of called AutoML, and which is really state-of-the-art topics. So rather than letting humans to kind of play with this, can we use data to guide us to perform principled hyperparameter tuning? So this is also really interesting state-of-the-art topic. All right, so just to summarize, we covered topology, we covered the loss and softmax layer, and also Backprop. And this is the third module.